Hello everyone, my name is Li Feifei from Tsinghua University Shenzhen International Graduate School. Today I'm happy to introduce our work Context-Free Grammar Inference for Complex Programming Languages in Black Box Settings. Our goal is to infer a grammar from a set of example streams and an oracle. The grammar we infer is a context-free grammar. A context-free grammar consists of non-terminals, terminals, production rules, and a star symbol. For example, this expression grammar can generate valid expressions. The oracle tells us whether a given string is valid or not. However, it is a black box, so we cannot access its internal logic. Existing approaches such as Avaza, Trivaza, and Kadava mainly use bubble merging to infer grammars. For example, given a string, we create a flat path tree. The path tree can be mapped to a grammar. Then we bubbling A as N1 and try to merge bubbles N0 and N1 to generalize the grammar. And the existing approaches are evaluated on relatively simple datasets. We extend the evaluation to more complex grammars, including C, C++, and Java. We evaluate against several state-of-the-art methods, including Avaza, Trivaza, and Kadava. These methods fail to produce useful grammars even after running for more than a week. After analysis, we identified two main problems: data decomposition and grammar construction. Data decomposition refers to breaking original examples into simpler ones for grammar inference. Avaza and Trivaza do not use data decomposition, which makes them slow and leads to overly complex grammars. Kadava uses the data decomposition but may lose the grammar structure during the decomposition process. The second problem is grammar construction. Avaza and Trivaza generalize poorly, making it difficult to infer complex grammars. Kadava requires perfectly correct grammars, which is unrealistic for complex languages. Overall, we need a method that can address both problems. So we propose the crucial. There is a crucial workflow. First, we segment streams, then build a decomposition forest from the segmentation. After that, we do lexical inference and grammar inference based on the forest. The key parts are decomposition forest and distributional matrix-based grammar inference. A decomposition forest is used to search short examples that satisfy given conditions. It solves Kadava's rule loss problem and improves speed. Distributional matrix-based grammar inference ensures limited accuracy while generalizing well. And now let me compare the data decomposition approaches in Kadava and Crucial. This figure shows the key difference. Kadava uses pre-decomposition before inference, which may lose grammatical structure. In contrast, Crucial uses decomposition during inference, guided by the current grammar, which helps preserve the structure. Then I will introduce the detail of the decomposition forest. It is used to find short sequences that satisfy given conditions. Here is an example of a decomposition tree. Each node represents a sequence. child nodes are simpler than their parent nodes. The tree starts with a single node and is gradually expanded during search. When building the tree, we start from the roots and look for child nodes that satisfy the given condition. We keep going until no more child nodes satisfy the given condition. Then we try some decomposition strategies to simplify the current node sequence. If the simplified example satisfies the given condition, the tree grows and we continue down. There are two main decomposition strategies. The first is removing subsequences from the sequence. The second is replacing long subsequences with shorter ones. Then I will introduce distributional matrix-based grammar inference. The method consists of three steps: computing the distributional matrix, building the swap graph, and merging selected bubbles from the graph. Here we choose 3, 5, and 7 to merge because they can swap with each other. After merging bubbles, the grammar is generalized. The distributional matrix represents substring context relations. It is constructed from all substrings and all contexts extracted from the current example set. Rows correspond to substrings and columns correspond to contexts. Each entry indicates whether placing a substring in a given context produces a string accepted by the oracle. A swap graph represents whether bubble can be swapped. Each node corresponds to a bubble, and an edge indicates that two bubbles can be swapped. Then I will introduce our experiments. We evaluate at 16 languages, 11 simple ones and 5 complex ones. This table shows their grammar sizes. Current datasets have about 7 non-terminals on average, while complex languages have hundreds. We compare with the current state-of-art methods Trivaza and Kadava. Our experiments answer 3 research questions: how accurate is our inferred grammar? How efficient is the method? Is the inferred grammar concise? Our first research question is about grammar quality. We measure precision recall and F1 score. Compared with Trivaza, we achieve 1.37 times better recall and 1.21 times better F1 score. Compared with Kadava, we achieved 1.19 times the recall and 1.13 times the F1 score. And crucial is the only method that works on complex languages. Our second research question is about efficiency. We measure runtime, oracle time, oracle quorums, and peak memory. Compared with Trivaza, we are 1.56 times faster, but use 1.68 times more oracle quorums. Compared with Kadava, we are 1.39 times faster, but use 1.99 times more oracle quorums. For complex languages, the crucial finish is in about 13.6 hours on average, while other methods of time out after 48 hours. Our third research question is about grammar readability. We measure grammar size and past performance. Compared with Kdava, Crucial produce the grammars with 1.11 times the non-terminals and 1.21 times the rows and 1.11 times the row length. This shows the crucial grammars are not much more complex than Kdava's. In summary, we introduce Crucial, a novel approach for context-free grammar inference in black box settings, and we compare the performance of Crucial against the state-of-art approaches Tripad and Kdava. Our results indicate that Crucial significantly outperforms these benchmarks in grammar quality and efficiency, and Crucial is the first method to infer complex grammars in practical time. Thank you for your listening, and I'm happy to answer any questions.